Hi everyone, the objective here is to simulate the flow about a circular cylinder numerically. Specifically, we're going to use a software called Ansys. Now, the Ansys student version is available for free. You can just download and install and play some basic stuff with it. Now, the objective here is just do something really basic, such that you get to know about what we mean when we say numerical simulation or computation with a CFD software. And CFD, of course, stands for Computational Fluid Dynamics. So the problem that we're going to work on, we have a rectangular domain. It's a 2D problem. So it's two-dimensional. It's also steady. So we don't consider any unsteadiness or turbulence, so we assume that the flow is basically laminar. And what we have is we have a circular cylinder here in our domain. The top surface and the bottom surface, they're rigid walls. So rigid wall and rigid wall here. Then we have an inlet, so the flow enters as a uniform velocity profile when it enters the domain. Of course, we take into account viscosity, so there's going to be no slip boundary condition close to the walls, upper and lower. And also cylinder has a rigid wall. So therefore, for the same reason, no slip boundary condition, the velocity of fluid particles on the cylinder, the velocity is going to be 0. And then the flow basically leaves the domain on the outlet side, which is on the right-hand side of the domain. All right, size of the domain. Let's consider the diameter of the cylinder to be 2, radius 1. And then the cylinder is at the center of the domain. So this distance is, let's say 10, and this distance is 10. Now, 10 meters, 10 inches, 10 feet, well, basically, we're going to see that it doesn't matter. The only thing that matters is the Reynolds number. So as long as Reynolds number has a specific value that we're interested in, it really doesn't matter. It's 10 meters or 10 kilometers or 10 micron and so on. Now, we want the walls to be far away from the cylinder such that the flow field about the cylinder is not affected by the walls, right? Now, where exactly the wall needs to be, 10, 100 times diameter, 5 times diameter, 5 million times diameter, well, it depends. First of all, it depends on how accurately we want to simulate the case. And again, also it depends on the Reynolds number, right? The lower the Reynolds number, you need to move the walls basically farther away. We start with 10, and there is a mechanism that we can talk about this. Again, I want to quickly just get you through some of the most important steps, or basic steps actually, to get the simulation going, and then we can come back and really talk about every little detail of the computational fluid dynamics. So let's assume that this distance is also 10, and then this distance is 20. All right. Now, again, there's a reason for that, because we don't expect the flow field to be affected, the upstream, which is here, to be affected by the presence of the cylinder very much, but downstream, of course, is going to be affected very much. So that's why we want the downstream to be a little larger. All right. So as I mentioned, the important parameter that we should pay a close attention to is the so-called Reynolds number, and that's rho VD divided by mu. Right? So let's say we want to work with Reynolds number equal to 2, because we want everything to be steady. So Reynolds number has to be pretty small. So there are two choices. In our simulation, we can set rho equal to 1. We can set mu equal to 1. D is 2. And V, let's set it equal to 1. And then with this choice of variables, of course, we get Reynolds number equal to 2. Now, this is good because, yeah, rho 1, mu 1, it's easy. V1, D2, it's easy to work with, right? Alternatively, you may say, no, I want to work with water. So Reynolds density is 1000, viscosity is 10 to the negative 3 about, diameter 2 meters. So what should be the velocity to get this equal to 2, right? And then you can basically just calculate what the velocity we need. And in this case, velocity is going to be, if I've done everything right, 10 to the negative 6. So you have to really enter 1, 2, 3, 4, 5, 6. meter per second into the code. And these two simulations, the above and the bottom, right, top and bottom, these two are going to give us exactly the same thing. There's no way for the software to understand the difference, right? As long as Reynolds number is the same, the result is going to be exactly the same. All right. Good. So let's get it started. We're going to do simulation with Ansys, as I said, and there are 4 different softwares we're going to work with. First is Design Modeler. All right, and there are other options that you can work with. Space Claim is the default. I'm a little bit more comfortable with Design Modeler, which is the older version, but it doesn't matter. It's basically the CAD part, the one that you draw this geometry. And then once we have the geometry and we define the domain and everything, right? So of course the domain is everywhere outside the fluid, outside the cylinder, and between the top plate and bottom plate and inlet and outlet. This is the domain. Now we need to divide the domain at the next step to smaller domains. This is called meshing or mesh generation, and mesh are those tiny domains that software basically can solve the equation pretty easily over that domain, and then the solution will be sewed together such that we have the entire solution for the entire domain. So the first is to design the geometry, the CAD part. The second part is to generate mesh or meshing or mesh the domain. The third part is or the third software we're going to work with is the solver, or the Fluent actually, which basically solves the governing equation. The output is a bunch of numbers, and we need the fourth software, which is the post processor, that basically gives us the pressure distribution graphs and the streamlines and everything that we can look at, and we can basically study the fluid flow. So after you install the software, what you need to do is to launch so-called workbench. All right, so you just basically click on and there you go, this is the workbench. Click on the start menu and just type workbench, and this should appear in your screen. Okay, so let's go step by step. So first, as I said, I'd like to work with Design Modeler. So I'm going to go to Tools, Options, Geometry Import, and instead, yeah, I'm already there. So okay, if it's a space claim, then change it to Design Modeler if you want to follow with me. Okay. Then we're gonna double click on Fluid Flow Fluent, or you can just drag this. As you can see, we have a large number of options. We can do acoustics, random vibration, rigid dynamics, static acoustics, and so on and so forth. We're interested in just one subset of different options that are provided, Fluid Flow. And again, for Fluid Flow, we have different options, but let's start with Fluent. So I'm gonna double click on this, and there you go. This is my project. I can double click here and I can basically choose a name. So let's call this project 1, say. Okay, and then I can click on geometry. Now these properties of geometry appear on the right hand side. If it doesn't appear, just right click and then you can choose properties here, right? What I need is to go in analysis type from 3D. Let's make it 2D. Okay, there you go, 2D. All right, so geometry, analysis type 2D. Now what I'm going to do, I'm going to double click on geometry, and hopefully if everything is working fine, it's going to open the design model for me. Let's see if that's happening. Yes, there you go. This is design modeler. All right, so first we're going to do a 2D simulation. We're only interested in X and Y, so I'm going to click on this. I just clicked on the z-axis, and now I'm going to see this I'm going to only see the XY plane. Then I go to here in the tree outline, I go to sketching, and I can go first to the setting and turn on grid showing 2D and a snap. So it's going to show the 2D grid, and my drawing is going to snap to these exact coordinates. If you want to zoom in, zoom out, there are different options. You can use your mouse and the keyboard, like a control, and move things around. Or you can just basically use the zoom in, zoom out, or pan to just basically move the coordinate up and down. Okay, now let's start by drawing our domain. So we want to have a rectangular domain. So I'm going to click on rectangle, and the size of the rectangle doesn't matter. It's better to have the center in between. As you're going to see, we're going to specify the size and location at the next step. So I'm going to start with this. All right. So this is basically my rectangle. You probably don't see the top part and bottom part, but it's there. Don't worry. Now, to specify the sizes and locations, we go to dimensions, click on vertical, select the x-axis, and then the top side of the cylinder. And as you can see, it shows you this symbol of dimension, right? And then I can move it a little further out and click. V1 appear here, and the value of V1 is here in the details view. V1 is 5 meters. I want V1 to be 10, right? So remember, from the center to the top is 10, and from center to the bottom is also 10. So as you can see, it automatically changes the shape of this rectangle to 10. Okay, we now do the same thing for the bottom part. Here, just pretty much here. V2 is 5, so I'm going to change that to 10 as well. All right, so now it's symmetric about here. Now it's turn for the horizontal dimensions. So I'll go from center to this side, and that one I want to be H3 scale. So I come here, H3, I want it to be also 10, enter. And then horizontal from the vertical axis to this one, and I want this one to be also, no, not also. I want H4 to be 20. 20. Okay. So if I just get rid of the grid, there you go. This is the domain, right? And actually, because I just specified the locations, I didn't need the grid. So this is my domain, and I can just make it a little larger so that we see what's going on here. Okay, next, well, we have the domain. It's time to put the circle. So I go to draw, circle. Now you can also read what you need to do at the bottom of the page. As you can see, it says click or press and hold for center of circle. So if I go around the circle, the center of the circle, the center of the origin, or origin, basically you see that it highlights the center. So I can just go, and you can make as large of a circle as you want or as small as you want. We're going to specify the exact size at the next step. Similarly, we go to dimensions, and you can say radius or diameter. Let's go with diameter. There you go. And just put it there. That's D5. I go here. The diameter, I want it to be 2. Boom. So this is a cylinder with diameter equal to 2. All right. Now, well, these are just basically a bunch of lines. Now I have to make a surface, and basically tell Ansys that where my domain is. So I'm going to go to concept, surface, surfaces from sketches, click. All right. And then I go here to X-plane, XY plane, sketch 1, and then I can go here and basically just apply. All right. And next, if I click on generate here, I see generate, then that's going to generate the surface. As you can see, Ansys automatically detects that, well, this is the area that we're interested in, and there is no domain inside the cylinder. We're not interested in the fluid flow inside the cylinder because cylinder has a rigid wall, right? Now, there are, of course, ways we can enforce that if the automatic detection doesn't work the way it should work. Now, one more thing we have to do quick here. So we go to the surface body, one part, one body, surface body in the tree outline. And here, fluid / solid, it's solid. Let's call it fluid. All right, and there's a thickness which is equal to 0. Make sure it's 0. That's it. We're good. All we need to do is to save this. I can just save here, Control S. It probably asked me for a name. Let's call it test2. There you go. So geometry is done. There's a check mark, green check mark here, and we're all set. The next step, as I said, is to basically mesh the geometry. So let's double click on mesh, and it's going to open the meshing software. That's going to generate basically mesh for us. Let's see, may take, okay, there you go. We got it. Okay. Oh, that was geometry. Okay, this is the mesh. If it's not a 2D, again, click on Z and it becomes, it shows you the XY plane. Now, well, as I said, the objective here is to divide the domain into smaller domain for which solving the equation, Navier-Stokes equation, is relatively easy. If you want to see what I'm talking about, just right click on mesh and you can just say generate mesh. So it's going to just generate without specifying anything. It's going to generate some like a default values, right? There you go. Mesh is generated. And this is really, I mean, it's a pure mathematics problem to how to generate an optimized mesh. As you can see, we go from a circular surface to a rectangular surface. What is the optimum way to do that? And there are, of course, many different ways or shapes or number of sides for the mesh that we're going to pick. So it's not an easy problem. So it's not that, it's a lot of work, right? Has gone into the meshing part of the system. But anyways, so let's move on. So we go to the geometry. We click on surface body. Let's make the thickness 0. We should do that. All right. And we generated the mesh already. Now let's maybe we can change the type of the mesh, so to triangular. And again, there are many different options, but let's go with triangular. Insert method, and let's click on the geometry, click here, and then you click on the yellow part and click on apply. All right, now the method currently is quadrilateral, and I want to change this to triangles. So triangles, there you go. And what I can do, I can go over the mesh and say, hey, update the mesh for me. There you go. Now the mesh is triangular. All you see, the mesh is triangular, and all you see is triangles in the domain. All right. So, well, again, this is a default. We didn't say how fine the mesh size need to be close to the cylinder, right? Now the cylinder is, the flow about the cylinder is what we care about, right? So this is actually the problem. So maybe we want the mesh to be finer. Now the finer the mesh, usually the more accurate the result, right? And this could be pretty coarse, right? So how can we make the mesh a little finer? Well, we can go here over mesh, insert, sizing. Now we have to select. We can select the entire volume. We can select surface. We can select an edge. So this is a 2D object, so we have to select edge. As you can see, as I get close to the cylinder, it turns into red. So I select this, and then I go here and apply. And element size, now this is where I'm going to specify the size of the mesh. As you can see, there are now 4. Now let's make it like 0.05 and enter. You see, the 4 elements now turned into tiny elements. Okay. Well, that's all. So then if I go to mesh and again select update, now the mesh, as you can see, is much finer, right? Much smaller. Now it's a compromise. So smaller mesh means more accurate results, but it's going to take longer time. This is a very basic problem, so it really doesn't matter much with the number of mesh that we have here. But if it's a complicated case, of course, every single mesh then matters, right? And you want to be very careful. Also, there's another parameter. We're not going to talk about all details, but as you can see, I mean, of course, close to the cylinder is the area that we care the most, and therefore we get less and less interested in the details of the flow field as we move away from the cylinder. So as you can see, the mesh is already big, but how this mesh goes from this small size to the big size is another parameter you can set. Is it going to go linearly? Is the size linearly grows or non-linearly? Or maybe the size is very small or non-linear or linear within a smaller boundary, and then after a certain threshold it starts to grow much faster or much slower. Again, these are all things that you can set. Some of them are based on experience, and some of them is there are some systematic method you can basically approach to be able to basically get to the optimum mesh. All right, now the next thing we have to do also here is to specify the boundary conditions. Remember, the top boundary, the top wall, the top boundary is a rigid wall, the bottom boundary is a rigid wall. This one is an inlet for which we're going to specify velocity. That one is an outlet. We don't want anything to come back to the domain from the outlet. So it can't be a wall. We can't specify the velocity. So there are tricks that basically we deal with this outlet boundary such that nothing comes back. And again, this is a difficult theoretical problem or mathematical problem. What kind of boundary condition we need to put here such that we don't have any reflection, or this boundary doesn't affect the flow field inside the domain? And believe me, it's not an easy problem. All right, so let's go with the edge selector and the top one, and I can hold the control key and click on the bottom, and then if you just right click and select create name selection, you can just push the N letter on your keyboard, and it says, oh, give it a name. So let's call this wall, right? And we don't specify the boundary conditions here. We just give names to these boundaries. Now, if you use some standard names, it's going to be very helpful, because later on Ansys is going to say, well, is it wall? So if you name it wall, Ansys understands it's a no-slip boundary condition. So it's going to help us with that at a later stage. But really, it doesn't matter. You can call it James or Hannah or Mark or whatever you want to call. All right. Now this one is, again, create name selection. We call it inlet. You can call it anything, but if you call it inlet, MATLAB says, yeah, with 90% chance you mean velocity is constant here. This one is outlet. Create name selection. Outlet. There you go. And well, we have another boundary. Don't forget the cylinder. And I'm going to call it cylinder. There you go. And we are all set here. Last thing is, let's do another update. Just make sure everything is good. And the mesh translation is sent to the workbench, so we can just get rid of the meshing. And see, this is a meshing in a CFD pre-post or whatever, prep post. So let's get rid of that and go back to the workbench. There you go. We are in the design model. We don't need the design modeler. We're back to the workbench and mesh. There you go. There's a check mark here. Okay. So the third software is the setup and basically the solver. So I'm going to double click on this. And Fluent launcher. So Fluent was an independent software, and it was bought by Ansys. So that's why it's Ansys Fluent. And really the core part of Fluent was this software that I'm opening now. In the old days, the meshing was done by another software called Gambit. I don't know if the software is still around or not. And then that was independent. And then you basically import the geometry to Fluent. But now everything is done here. Dimensions already we said 2D. Display mesh after reading and options. Let's go with double precision. Yeah, sure. Display mesh after reading. Show it, it's okay. Now parallel, if you have a local machine, it depends on how many processors you have. So in my laptop, I'll have 8, so I can go with 4. So it automatically becomes a little faster. GPU machines and learning resources, you can just browse and learn about this. Again, we want to be quick here. So let's start. Okay, so this is our solver. Now, what we're going to do, we're going to go to the setup, the general, and then the solver, pressure base is good, velocity, formulation absolute, planar is good, time is steady, transient is steady. So if it's unsteady, we're going to go with this. Everything looks good here. Now, then we go to setup models. And basically, there are different options provided here. You can double click such that it appears in the task page, or you can just basically click on the plus sign here and it opens up. So what we want is a viscous laminar. So things have changed a little bit here. Let's see what we have. Viscous SST, multi-phase energy, viscous. This is a turbulent radiation heat species, discrete phase. So let's go with this one. And let's see what kind of options it gives us. There you go. All right, it's here. Oh, okay, so the option is here. So in the old versions, if you have the old version, the viscous laminar appears here. But now I have to say viscous and then choose if it's inviscid, laminar, and then these are the Reynolds models that we have, K epsilon, K omega, Reynolds stress, and so on. Okay, so this is now laminar, viscous laminar appeared here. That's good. All right. Now I can make this smaller. Let's go to the material, and for the fluid, well, it says it's air by default. So let's open the property page, and I can just name it whatever, air, water, mercury. As we said, as I said, I want to make the density equal to 1 so that the Reynolds number is 2 and viscosity also 1. Okay, so, and I call this like maybe water. It's okay. Change create. So now it's whatever material that you have is density is 1, viscosity is 1. Change create. Did I press this? Yes, close. So we're good with the material. We don't have any solid. All right. Now the next is to go to the boundary conditions. Let's bring here boundary conditions. And then I can just double click such that the boundary condition opens the task page. Well, what is cylinder? Well, automatically says here the type is wall. That's exactly what we want. You see, you have different options: mass flow, outlet, inlet, pressure, symmetry, this. But it is a wall, no slip wall. So that's good. Let's keep it there. Yeah, I don't need any to move this. And then inlet, let's first look at the wall. So wall, the type again is detected automatically to be wall, so I keep it there. Now inlet, well, automatically says it's velocity inlet. Sure, this is what we want. And then to specify the velocity, I just click on edit, and the velocity magnitude is just 1. All right, normal to the boundary. That's what we want. And again, the different options. Apply. So the velocity is now 1. Close. Interior surface body, that's the interior of the domain. Just a general interior is a good one. There are different options if it's a porous material, but we don't have porous material in our system. And then the outlet is a pressure outlet. Again, we have a long list of options. Each one requires long discussion. But the default pressure outlet is good enough. All right. So boundary condition is good, and I think we're pretty much ready to, if I don't want to tweak anything else, to just get this to work. Mesh interface dynamic, mesh reference values, and solution method. Let's look at the method. Coupled, okay, that's good. Controls, report, monitors, and we can't go over the rest, but we can just move ahead to the initialization. We always have to initialize the code, and hybrid initialization is good. Let's just initialize, and it's a very fast step. And then we're ready to run calculations. So if this is your first time to calculate, to run a CFD, so that's going to be fun. Time step method, automatic, everything is good. Reporting interval 1, time scale factor, let's see, check case, time step method, automatic, verbosity, number of iterations. So we want this to be iterated, say 100 times, right? That's a maximum. So if a convergence is achieved, if the good solution is found, it's going to stop before that. So 100 times is good. And I think I'm good here. So you can just push the calculate. And if we're doing everything right, it's going to start to iterate the solution to get to the actual one. So calculate. And yeah, it's calculating the error. Boom, boom. That was pretty fast. Again, this is a very simple problem. Steady, low Reynolds number, not huge mesh, but we got that. So what you saw a little bit here was the scaled residuals. And this is basically the error. And as you can see, the error is nicely going down, right? And at some point, based on the default values, just said the error is small enough that I'm going to stop. Okay, the solution, we're done. The solution is already worked out. We're done with Fluent. And again, this is super easy problems. We're talking in real life, we're talking about problems that take sometimes months to run on supercomputers, but this is an easy problem. All right. So as you can see, we have a check mark on setup and solution, and we can just go to the result. So let me double click on this to open the post-processing. All right. Let's just get these ones. Give me 1 second. It's loading. And there you go. Okay, load on the other screen. Okay, so this is our domain, and I click on Z, so I see what's happening here. So there are different things we can plot. Just quickly, let's see if we can plot the contours of velocity. So I'm going to click on contour, and let's call it contour 1. Some properties appear here. On the domain, I'm going to call surface body. The location, let's put symmetry 1, so it's going to show us the entire dimension. The variable, let's just first plot the velocity, the total velocity. And the range, I think it's good to be global. And if I press apply, it's going to show me the plot, the contours of velocity for this problem out of the CFD problem that's been solved. There you go. This is the contours of velocity. And this is the cylinder. Of course, velocity above the cylinder is higher, below the cylinder is lower. Now, this is not very accurate. So if you want to increase the number of contours from 11 to say 20, we can certainly do that and apply, and it's going to be finer. Let's make it 50. It's going to take a little longer time, but it's going to be finer velocity profile. And I think the maximum is maybe 99. Yep, we got the 99, and let's see if 100 works. Yeah, 100 works. I don't know how far we can go, but again, this is a contours. This is the plot of velocity. Now, if you want the velocity in the x direction, yes, sure, we can do that. This is just velocity in the x direction, which is very similar to the total velocity. How about velocity in the y direction? Well, then it's going to be opposite, because above the cylinder, velocity is upward, right? Fluid particles is going upward, and here fluid particles is going downward. So that's why the colors are opposite. And if you want to plot pressure, there you go. This is the pressure, right? And there's a stagnation point in front. Right, maybe this is a little better, or maybe this one. It's a stagnation point here, and because of separation, we have a low pressure behind the cylinder, and that's why we get basically the resistance. So just play with these different values here and see what you get. So there was pressure, we keep it there. Now, one more thing is, let's plot Streamline. So if you go here after contour, if you just stay on this icon, you see a Streamline. So if I click here, Streamline 1, good. So 3D Streamlines, domain, all domain, let's say surface body. It says, okay, you want the Streamline to start from where? So let's say I want to start the Streamline from inlet. And equally spaced, number of points 25. I think everything is good. Velocity, it's gonna color it with that. And I just need to turn off the contours so that I can see the streamline. So I'm gonna turn off the contours. And if I apply, there you go. The streamlines are there. I can make also a larger number of streamlines. Maybe that's too much. I'm afraid it may slow down the computer very much. Okay, this is 100 times 100 points. Streamlines starting from 100 points, and on top of the streamline, the color is the velocity. I can change that to say where is the color? Somewhere has to be, yeah, the color is here, right? That you can basically set how it varies. Now, I can also say start from the surface body. Let's see if it works. So this is from the inside. Maybe I say start from symmetry 1. Let's see. Yeah, that doesn't work as well. So yeah. I expected this. Yeah, this is, oh, I'm sorry, this is already 25. So let's say 100 start from surface body. It randomly starts from inside the domain. So that's going to be more, right? Now we see the behavior on the downstream of the cylinder even better. So if I like this, make this 500, I hope it doesn't crash. There you go. Okay, so we have even higher number of streamlines. And if I just further zoom in, you see the behavior about the cylinder even better. All right, so there you go. Again, you can just play with and consider this a really very first CFD simulation. As I said, it's a lot more complex. You saw so many options we have at every step. And I mean, yes, every even high school kid can run something, but really doing something good simulation that you can trust on simulation based on which you can design an airplane or a bridge requires a lot of experience, a lot of careful evaluations and validations and cross validations and so on and so forth. All right, so if time permits, I'm going to post more videos, but for now, you've done your first CFD simulations, and I hope you enjoyed it. Thank you.